Hey, and welcome to the second part in the rumprun-unikernel video series. This is chapter 2, the 3 commands. So, in the first part, we took mpeg123, turned it into a unikernel, ran it, and produced sound that way. But we sort of just rushed through the commands and we didn't really pause to explain which command does what. So, the purpose of this second part in the series is to go over those commands which we used previously and sort of explain what they are, why they're done that way, what options they take, and give you an idea of how you can vary the commands and remix things and vary the parameters to better produce a unikernel which you actually need and want. So that's what we're going to look at. We're also sort of going to brush on the experimentality of each of those commands in detail so you can get an idea of what's perceived to be stable and what might still change. And if something remains unclear, you can always ask a question on the mailing list, or even if you think there's a good subject to cover on a later episode of this show, you can send a suggestion in private email to me. I won't answer technical questions in private email, but I will make a note of any good questions and might cover them on later shows. Okay, so with that out of the way, let's get started. So first of all, if you want to follow along and happen to have a checkout from the previous episode, you might want to pull a new one and update. As part of thinking about what I'd say, I noticed that, hey, if there was a command which did this, it would be a lot easier to explain something, so I added a few things here and there. If you want to make sure you have at least a good enough version, this is the rumprun checkout or revision I will use. Okay, cool. So first up is build-rr. As mentioned previously, this builds the compiler. This builds the operating system, or what would be in classic terms perceived to be the operating system. Now, in the optimal case, you wouldn't need to use this command at all. You'd simply install the correct binaries for your host system, and that would be the end of it. But since I assume most host systems don't at least yet provide binaries for this in their packaging systems, we'll go over this stuff. So let's actually start about discussing compilers. So to compile an operating system, you obviously need a compiler. Usually that compiler needs to come from somewhere. Now, we don't ship a compiler. So you bring the compiler, we deal with it. That's kind of the mentality. Why do we do that? Well, first of all, it's very simple for us because we don't have to maintain compilers. Second of all, it's flexible for you because, you want to use a certain version of a certain compiler or whatever. If we just pick one for you, that might not work. But if you bring your own, hey, it might work. So let's start dissecting the options that this command takes from the compiler. So by default, or let's say if you run this like we ran it last time, like this, don't specify any compiler. So what actually implicitly happens is this. So like this bit of the usage says the toolchain is picked up from the environment. So that's what that means. I hope the wiki probably explains in more detail. But anyway, this is what happens. So if we examine the CC on this machine, it says x86-64. And that's all we really care about. So a compiler does two things. It generates code for the target machine architecture, then it does an operating system specific bits. We actually only care about the target architecture. We try to undo the operating system bits and add our own. And I mean, if we didn't do that, you'd have to build your own compiler, which, like I mentioned earlier, or explained earlier, is a bit complicated and unnecessary. So we essentially just care about the target machine architecture. So if we run things like this, I'll actually have to pause this because there's no convenient way to display. Crap. I also should run it correctly. Pause it here. So you see it says it's building for AMD 64, and this machine and machine architecture is NetBSD terminology, but anyway, 64-bit x86. And okay, so that's essentially how the target machine architecture gets selected. Now I happen to have another compiler here which is targeted for NetBSD, but it's as you can see, it's ARM compiler, and this helps when you spell things correctly. The target tuple is completely different. So if we give this compiler as an argument to the command and run it, and then we can see that it's building for a completely different machine. So essentially that's how you select your target, or that's how this script selects what kind of binaries it's going to build and what kind of architecture the target will be. Now if you happen to know ARM, you know that okay, this is not enough to uniquely specify which ARM system you're building for, and I'll get to that in a moment. But meanwhile, let's look at the other commands this script offers. So there's essentially, in addition to the compiler, which is passed like that in the environment, there's 4 groups of parameters you can pass. There's some flags you can build to a non-default destination directory. You can use a non-default object directory. You can use a non-default source directory. If you're a developer, you probably have an idea what you can use these for. If not, then you don't have to care about them. There's an interesting flag -k, which is listed down here in expert only options. It means build the kernel only without libc and tools. This is when you want to develop a really tight package without the POSIX application stuff getting in your way. If you don't know that you need -k, then it's another thing which you then don't need. Then you specify the platform, hardware or Zen. Last time we used hardware, then we ran it under KVM, worked fine. If you want to run per-virtualized Zen, then you specify Zen here. Now, when I talked about ARM, this is somewhere where we probably should somehow be able to indicate what board you're building for. So when you're building for x86 hardware, it's sort of a generic system, so there's only one type of x86 really, well, 32 and 64-bit, but anyway, and they can pretty much all boot using the same code. If you're in ARM land, it's completely different, so the boards are vastly incompatible, so we would have to have some mechanism here to specify which actual ARM board you're building for. And we'll probably change this option at some date, but that day hasn't come yet as of today. Okay, so the third group of options is install actions, and it can be either build or install or both or neither, which logically means both. So the idea is simply you can do an unprivileged build, then you can sudo install. And it's sort of a good idea if you specify all the same parameters in both build and install. I mean, in theory, you should only have to specify the same object directory because the parameters should be picked up from there, but I'm not actually sure if it works. If it doesn't, you can try it and file a bug report, and someone will fix it someday. Then the last thing here is build-rr.sh options. Now, first of all, what's build-rr.sh? Well, so the rumprun unikernel uses rumkernel as the underlying driver components. So the TCP/IP stack, the POSIX system call handlers, the file system drivers, all that is provided by rumkernels, and we just use them, which is part of the reason why this whole operating system is just around 10,000 lines of code, because almost all of it is drivers which come from rumkernels. So we get them for free essentially. And build-rr.sh is the portable script to build rump kernels. And actually there's even, without going into too much detail, there's actually even 2 layers of toolchain. So this build or rumprun build script creates the application toolchain, which uses toolchain wrappers created by build-rr.sh, which uses the actual backend toolchain. So when we specify cc equals foo, that actually is handled by build-rr.sh. But anyway, we can see what kind of options it takes, and the most useful ones are these flags which these toolchain flags which you pass to the compiler, assembler and linker. So again, without going into too much detail, you can do something like this, where you say do a 32-bit build. So this my compiler, as you remember, targeted the x86-64 by default. Usually they, or I guess always, you can tell them to build for the 32-bit architecture by passing this flag. So if we pass that flag, I'll again run this and pause it. So you notice that now it's building for i386. So for example, if you're in ARM land, you want to specify your ARM target exactly, and you have some compiler. That's how you do it. Okay, I wonder if there was something more I should discuss about build-rr. Probably not. So yeah, so let's move to the next step. So let's now start. So now we sort of have the compiler and operating system again. I've pre-built these now, so I don't have to run the build script. And how do we build applications? How do we build the unikernel? So to do that, let's just start with the simple hello world program, which if we just inline write one, guess that's good enough. So we can compile this, of course, natively, and we can run it, and it even prints the expected result. Woohoo! Yeah. So what if we want to turn this into a rumprun unikernel? I mean, I'll just use this hello world as an example program because it's simple, and you know, we don't. Last time we used mpeg123, the same principles apply, but this is just simpler to explain. So let's delete that. So as part of the build process, this toolchain wrapper was created. Now the name depends on which architecture you want, and or which architecture you built for, and like I said previously, or in the previous video, this toolchain is, or the name of this toolchain is printed at the end of the build-rr invocation. So if you're not sure, you can run build-rr and check there. Okay, but this works exactly like a regular compiler. So what was really important for us, and I already stressed it in the previous video, was to get things compiling exactly like they would when you build a regular application, because that way, in the ideal case, you require 0 modifications to the build systems. And that's useful. Build systems are really hard to modify, especially when they tend to do trivial things and or kind of be against the grain and not really your standard build system. So if you don't need modifications, if things at this stage look exactly like you're compiling a regular application, it's awesome, because then, you know, we can skip a lot of problems, or actually you as the user can avoid a lot of problems. So yeah, so let's compile this just like previously, except the compiler name is different. Cool, screen corruption again. And what we end up with is a.out, which happens to be executable. Can we run it? Well, we can try, but it won't work because it's not a Linux binary, it's a rumprun unikernel binary. There's actually a funny reason why it's executable. Some build system refuses to believe that the C compiler works if it doesn't create or if the created file doesn't have the execute bit on, so that's why we have to keep the execute bit on, even though you can't execute it, which is really a silly requirement anyway. If you're cross-compiling, you know, your compiler won't create anything which is executable locally anyway. So but essentially that's what we're doing. We're cross-compiling. Okay, but this is just the application bit, so nothing else. This stage looks exactly like compiling a regular application. Now here's where it gets different, and this is how I usually try to explain it. So imagine you have an application which runs on the operating system. Now how things work out is that you boot your operating system, and then you implicitly have the context, the drivers, the mechanism for executing binaries and so forth, in which you run your applications, and that's which ties the application to your operating system. Now in the case of rumprun, it's a unikernel, everything is mashed together, so we don't separately boot an operating system and an application. We boot them both in unison. So we need some mechanism to attach the operating system bits to this binary, which was compiled exactly like you'd compile any other binary. And for that we use the rumprun-bake tool. Now if you remember how we used it previously, for MPEG 123 in the previous video, we did something like this, and that does the baking. Now what's actually happening here? So let's just delete that. So first of all, if we run this command without any options, we see the usage here, and first one is list, next is describe, and then there's a third one which actually does something. So they're explained here. List outputs available configs, describe output details for the given config, and then the third one is which creates the actual image. So after this rumprun-bake step, we have an image which we can boot on the guest, and it will run and work. So yeah, let's figure out what's going on. So if we run rumprun-bake list, we get a list of different configurations. So for example, you have Zen PV, which is Zen with paravirtualized drivers, or you have hardware virt.io SCSI, which is virt.io with SCSI. So this and well, then you have generic, which is the generic one, which we gave previously, or which we used previously. Okay, let's try the describe subcommand. So let's describe virt.io, let's say. It prints a list of parameters, and then since this is Unix, we can sort of make it a bit more readable, or whatever we want. But essentially you see, well, I don't know what you see, but I mean, this makes complete sense to me. But what these are essentially are excuse me, they're linker parameters, or we treat them as linker parameters. What they're meant to be are the operating system components. So again, in this step we're attaching the operating system to the application, and this is just a list of the operating system components we're attaching. So we know that if we attach with the excuse me, with this particular configuration, we can, for example, mount file system images, or we can do we have the support for virt.io drivers. So this essentially just specifies the operating system. Now if you want to know in depth about what each individual component is, there's a trick. So you can go to source.net BSD rump, then we use make wrapper, which was created by build-rr.sh, which is rump make, which is just a variant of make which is used to build rump kernel components, and we give it the rump describe target. That's actually not good. That's definitely not good. I probably forgot to actually do a build, so I'll run the build, or I'll pause the video, run the build, and then come back. Okay, done. So actually I think I know what happened. What happened is when I was demonstrating how the compiler gets picked up from the environment, I interrupted the build at a bad time, and then it just we didn't have the wrapper available. Anyway, let's try again. If it still doesn't work, then I guess you get your money back. Nope. Rump describe. Yes, actually, if we grep out the make spam from that, we can see better. So what this command produces is a list of all the driver components here, and then produces a short description for each one. So for example, rumpnet net 802.11 gives you 802.11 subroutine support, and in the rump-bake configuration you just have it would be listed like this. So essentially you put -l in front and then get a library. Okay, yeah, so let's go back here. So let's go back to rumprun describe, no, rumprun-bake, which was the rumprun-describe command. So, you know, now you can cross-reference these against the list I showed you previously. If something is wrong or right, then or if there's something extra or something's missing for what your needs are, then or you can figure that out. So yeah, so one more thing about rumprun-bake. So we're attempting to make it modular. We're sort of part way there. I'm not sure we're completely finished, but the idea is that you can take existing configurations, add components, remove them fairly easily. So I forgot the version. So rumprun-bake, if you run it, it prints a version. So you can see here we're already attempting a bit of backward compatibility. We've given it a version number, and I'm not exactly sure we'll still support everything back to this version number, but we might, who knows. Oh, and about the compiler's experimentalness, that's completely solid, because it works exactly like for the regular case, so we couldn't actually hope for anything better. It's perfect. Yeah, so let's I forgot it again. Well, I hope I remember it. Let's write a configuration file. So what we can do is create a configuration file. Then there's a command called assimilate, which you can use to assimilate existing configurations into your new configuration. So let's say we base this on virt.io. Then we can remove, for example, the CD driver. So now this should give us a configuration called hwmyconf, which is exactly the same as virt.io, except with this component removed. Let's see. Oh, one thing. Currently, the name of the configuration needs to begin with the platform's name, because the toolchain, as you can see, doesn't contain any indication of the platform. So this is the first stage where we're attaching the platform to the whole concept, and the name of the configuration of rumprun-bake is how we currently do it. I hope that makes sense. It makes sense, just I don't know if I explained it very well, but if I didn't, again, you don't, you get your money back. Yeah, so we specify an alternative configuration file. If we list, then we see now we have this hw-myconf, and we can describe it, and if we format it a bit nicer, you can see that between here and here there is no CD990 component, as opposed to if we do it this way, then you can see it is there. Oh yeah, well, I forgot how the alphabet goes. Actually, C comes before E. Yeah, things happen. Well, anyway, so now we can use, for example, that configuration to bake our application, i.e. attach the operating system to it, and I hope this works. myconf, let's call it a.bin and a.out. Okay, so essentially now, again, we have a fairly large a.bin, but that's because all of the components we attach to it are actually compiled with debugging symbols. So if we want to make it smaller, we use, and this is what I did incorrectly in the previous video. I should have used this as the strip. Instead, I used the host strip directly. It happened to work for this particular system. It's not guaranteed to work universally. Okay, so there we go. So it's a bit smaller. Yeah, so then the only remaining thing is to run that program as a guest. Now, as I said previously, there's a tool called rumprun, which is a launcher, and the purpose of that tool, so if we imagine the compiler wrapper x86-64 rumprun netbsd gcc compiles the application. Rumprun-bake attaches the operating system to it. What else do you usually need? You need the operating system, first of all, to be booted, and second of all, you need the operating system to be configured. So you usually have some sort of RC scripts in an operating system. And then you log in with SSH and VI all around Etsy, and then, you know, eventually you have sort of a configured operating system. So when you boot it, it's sort of in the correct configuration. You know, you have the correct routing table information set up, you have the correct IP address, you have the correct file systems mounted at correct points, and so forth. So we need some similar mechanisms in our system too. Now, currently we use this rumprun tool, which prints out a fairly long usage, and this has currently a dual function. So it both attaches the configuration and it sort of launches the guest. Except if I scroll up, you can see there's a bunch of different guests. Like there's a create a directory with contents necessary for Amazon EC2. So essentially you can, from those contents, those have the configuration you specify to this command attached to them, and then you can do something else to create the AMI and then launch it. So for example, in that case, you don't really run anything. The other thing is you create a bootable image. Again, you don't run it, but you attach the configuration to it. But for example, in the KVM case, we specify the configuration and launch the guest. So this is sort of where this command went wrong, because it has a dual function, both configuration and launching, and it just doesn't work for all possible backends. So we're sort of looking how to redo this. Well, but anyway, you can, I mean, currently this is the official way to launch things, so I think I'll just launch the hello world we built, and then I guess we'll leave it at that. So let's say KVM, let's do it interactive. Someone actually, was it a week or two ago, I was chatting with someone and they told me another way to use a sort of serial console. So if you pass dash curses to QEMU, it, instead of opening a new window, it just maps the VGA console to curses, and then you can get it displayed in your terminal. So what this does is rumprun KVM, which says launch it as QEMU enable KVMs, and then -G passes all of the arguments to the backend, which in this case is QEMU. So essentially this is running QEMU. Actually, I'll show you. So if you pass -D here, you'll actually see what's going on. So this is how QEMU would be launched. Actually, let's just try running that manually, because I like to maximize demo effects. This is where it gets tricky. I don't actually know how that will work. Well, let's see. I really need to stop improvising. Well, it seemed to work. Woohoo! So I got lucky. So you see it's sort of a weird color, but you can see the hello here, which is what we were expecting. Okay, so I think that was pretty much it. Yeah, if you think I missed something, or have suggestions on what to cover in a future episode of this series, drop a note. Otherwise, try this stuff out for yourself and take care.